By now, you've seen a range of different learning algorithms. Within supervised learning, the performance of many supervised learning algorithms will be pretty similar, and what matters less will often be whether you use learning algorithm A or learning algorithm B, but what matters more will often be things like the amount of data you train these algorithms on, as well as your skill in applying these algorithms, things like your choice of the features that you design to give the learning algorithms and how you choose the regularization parameter and things like that. But there's one more algorithm that is very powerful and is very widely used both within industry and in academia, and that's called the support vector machine. And compared to both logistic regression and neural networks, the support vector machine, or the SVM, sometimes gives a cleaner and sometimes more powerful way of learning complex nonlinear functions. And so I'd like to take the next videos to talk about that. Later in this course, I will do a quick survey of a range of different supervised learning algorithms just to very briefly describe them. But the support vector machine, given its popularity and how powerful it is, this will be the last of the supervised learning algorithms that I'll spend a significant amount of time on in this course. As with our development of other learning algorithms, we're going to start by talking about the optimization objective. So let's get started on this algorithm. In order to describe the support vector machine, I'm actually going to start with logistic regression and show how we can modify it a bit and get what is essentially the support vector machine. So in logistic regression, we have our familiar form of the hypothesis there and the sigmoid activation function shown on the right. And in order to explain some of the math, I'm going to use Z to denote theta transpose X here. Now, let's think about what we would like logistic regression to do. If we have an example with y equals 1, and by this I mean an example in either the training set or the test set, or the cross-validation set. But if y is equal to 1, then we're sort of hoping that h of x will be close to 1. So, right, we're hoping they'll correctly classify that example. And having h of x close to 1, what that means is that theta transpose x must be much larger than 0. So this greater than sign, that means much greater than 0. And that's because if it's z, that is theta transpose x, is when z is much bigger than 0, is far to the right of this figure, that the output of logistic regression becomes close to 1. Conversely, if we have an example where y is equal to 0, then what we're hoping for is that the hypothesis will output a value close to 0, and that corresponds to theta transpose x, or z, being much less than 0, because that corresponds to the hypothesis outputting a value close to 0. If you look at the cost function of logistic regression, what you find is that each example, x comma y, contributes a term like this to the overall cost function. Right, so for the overall cost function, we usually we would also have a sum over all the training examples and a 1 over m term. But this expression here, that's the term that a single training example contributes to the overall objective function for logistic regression. Now, if I take the definition for the form of my hypothesis and plug it in over here, then what I get is that each training example contributes this term, right, ignoring the 1 over m, but it contributes that term to my overall cost function for logistic regression. Now, let's consider the two cases of when y is equal to 1 and when y is equal to 0. In the first case, let's suppose that y is equal to 1. In that case, only this first term in the objective matters, because this 1 minus y term will be equal to 0 if y is equal to 1. So when y is equal to 1, when in our example x comma y, when y is equal to 1, what we get is this term, minus log 1 over 1 plus e to the negative z, where, as similar to the last slide, I'm using z to denote theta transpose x. And of course, in the cost, we actually had this minus y, but we just said if y is equal to 1, so if that's equal to 1, I just simplified it away in the expression that I have written down here. And if we plot this function as a function of z, what you find is that you get this curve shown on the lower left of the slide. And thus we also see that when z is equal to large, that is when theta transpose x is large, that corresponds to a value of z that gives us a fairly small value, a fairly small contribution to the cost function. And this kind of explains why when logistic regression sees a positive example with y equals 1, it tries to set theta transpose x to be very large, because that corresponds to this term in the cost function being small. Now, to build a support vector machine, here's what we're going to do. We're going to take this cost function, this minus log 1 over 1 plus z to the negative z, and modify it a little bit. Let me take this point 1 over here, and let me draw the cost function I'm going to use. The new cost function is going to be flat from here on out, and then I'm going to draw something that grows as a straight line, similar to logistic regression, but this is going to be a straight line in this portion. So the curve that I just drew in magenta, the curve that I just drew in purple and magenta, so it's a pretty close approximation to the cost function used by logistic regression, except that it's now made up of two line segments. There's this flat portion on the right, and then there's this straight line portion on the left. And don't worry too much about the slope of the straight line portion. It doesn't matter that much. But that's the new cost function we're going to use for when y is equal to 1. And you can imagine it should do something pretty similar to logistic regression. But it turns out that this will give the support vector machine computational advantages and give us later on an easier optimization problem that will be easier for software to solve. We just talked about the case of y equals 1. The other case is if y is equal to 0. In that case, if you look at the cost, then only this second term will apply, because the first term goes away, right? If y is equal to 0, then you have a 0 here, so you're left only with the second term in the expression above. And so the cost of an example, or the contribution of the cost function, is going to be given by this term over here. And if you plot that as a function of z, so I have here z on the horizontal axis, you end up with this curve. And for the support vector machine, once again, we're going to replace this blue line with something similar. And in particular, I'm going to replace it with a new cost, this flat out here, this 0 out here, and that then grows as a straight line, like so. So let me give these two functions names. This function on the left, I'm going to call cost subscript 1 of z, and this function on the right, I'm going to call cost subscript 0 of z. And the subscript just refers to the cost corresponding to when y is equal to 1 versus when y is equal to 0. Armed with these definitions, we're now ready to build the support vector machine. Here's the cost function j of theta that we had for logistic regression. In case this equation looks a bit unfamiliar, is because previously we had a minus sign outside, but here what I did was I instead moved the minus signs inside this expression, so it just makes it look a little bit different. For the support vector machine, what we're going to do is essentially take this and replace this with cost 1 of z, that is cost 1 of theta transpose x. And we're going to take this and replace it with cost 0 of z, that is of cost 0 of theta transpose x, where the cost 1 function is what we had on the previous slide that looks like this, and the cost 0 function, again, what we had on the previous slide that looks like this. So what we have for the support vector machine is a minimization problem of 1 over m, sum over my training examples of yi times cost 1 of theta transpose xi plus 1 minus yi times cost 0 of theta transpose xi, and then plus my usual regularization parameter like so. Now, by convention, for the support vector machine, we actually write things slightly differently, or we reparameterize this just very slightly differently. First, we're going to get rid of the 1 over m terms, and this just happens to be a slightly different convention that people use for support vector machines compared to for logistic regression. But here's what I mean. What I'm going to do is I'm just going to get rid of these 1 over m terms, and this should give me the same optimal value for theta, right? Because 1 over m is just a constant. So, whether I solve this minimization problem with 1 over m in front or not, I should end up with the same optimal value for theta. Here's what I mean. To give you a concrete example, suppose I had a minimization problem that minimize over a row number u of u minus 5 squared plus 1, right? Well, the minimum of this happen to know the minimum of this is u equals 5. Now, if I were to take this objective function and multiply it by 10, so here my minimization problem is min over u of 10 u minus 5 squared plus 10. Well, the value of u that minimizes this is still u equals 5, right? So multiplying something that you're minimizing over by some constant, 10 in this case, it does not change the value of u that gives us, that minimizes this function. So in the same way, what I've done by crossing out this m is all I'm doing is multiplying my objective function by some constant m, and it doesn't change the value of theta that achieves the minimum. The second bit of notational change, which is just again the more standard convention when using SVMs instead of logistic regression, is the following. So for logistic regression, we had two terms to the objective function. The first is this term, which is the cost that comes from the training set, and the second is this term, which is the regularization term. And what we had was we controlled the trade-off between these by saying, we wanted to minimize a plus, and then my regularization parameter lambda, and then times some of the term b, where I guess I'm using a to denote this first term, and I'm using b to denote that second term, maybe without the lambda. And instead of parameterizing this as a plus lambda b, we could, and so what we did was by setting different values for this regularization parameter lambda, we could trade off the relative weight between how much we want to fit the training set well, that is minimizing a, versus how much we care about keeping the values of the parameters small. So that would be the parameters b. For the support vector machine, just by convention, we're going to use a different parameters. So instead of using lambda here to control the relative weighting between the first and second terms, we're instead going to use a different parameter, which by convention is called c, and we're instead going to minimize c times a plus b. So for logistic regression, if we set a very large value of lambda, that means give b a very high weight. Here is that if we set c to be a very small value, that corresponds to giving b a much larger weight than a. So this is just a different way of controlling the trade-off, or just a different way of parameterizing how much we care about optimizing the first term versus how much we care about optimizing the second term. And if you want, you can think of this as the parameter c playing a role similar to 1 over lambda. And it's not that these two equations or these two expressions will be equal if c equals 1 over lambda. That's not the case, but rather is that if c is equal to 1 over lambda, then these two optimization objectives should give you the same value, the same optimal value for theta. So just filling that in, I'm going to cross out lambda here and write in the constant c there. So that gives us our overall optimization objective function for the support vector machine. And if you minimize that function, then what you have is the parameters learned by the SVM. Finally, unlike logistic regression, the support vector machine doesn't output a probability. Instead, what we have is we have this cost function, which we minimize to get the parameters theta. And what a support vector machine does is it just makes a prediction of y being equal 1 or 0 directly. So the hypothesis will outpredict 1 if theta transpose x is greater than or equal to 0, and it'll predict 0 otherwise. And so having learned the parameters theta, this is the form of the hypothesis for the support vector machine. So that was a mathematical definition of what a support vector machine does. In the next few videos, let's try to get better intuition about what this optimization objective leads to and what are the sorts of hypotheses a SVM will learn. And we'll also talk about how to modify this just a little bit to learn complex non-linear functions. Sometimes people talk about support vector machines as large margin classifiers. In this video, I'd like to tell you what that means, and this will also give us a useful picture of what an SVM hypothesis may look like. Here's my cost function for the support vector machine, where here on the left, I've plotted my cost1 of z function that I use for positive examples, and on the right, I've plotted my cost0 of z function, where I have here z on the horizontal axis. Now, let's think about what it takes to make these cost functions small. If you have a positive example, so if y is equal to 1, then cost1 of z is 0 only when z is greater than or equal to 1. So in other words, if you have a positive example, we really want theta transpose x to be greater than or equal to 1. And conversely, if y is equal to 0, we look at this cos0 of z function, then is only in this region, where z is less than or equal to 1, that we have that cos0 of z is equal to 0. And this is an interesting property of the support vector machine, right? Which is that if you have a positive example, so if y is equal to 1, then all we really need is that theta transpose x is greater than or equal to 0, and that will mean that we classify it correctly. Because if theta transpose x is greater than 0, our hypothesis will predict 0. And similarly, if you have a negative example, then really all we want is that theta transpose x is less than 0, and that will make sure we got the example right. But the support vector machine wants a bit more than that. It says, don't just barely get the example right? So then don't just have it just a little bit bigger than 0. What I really want is for this to be quite a lot bigger than 0, say maybe greater than or equal to 1, and I want this to be much less than 0, maybe I want it less than or equal to -1. And so this builds in an extra safety factor or safety margin factor into the support vector machine. Logistic regression does something similar too, of course, but let's see what happens, or let's see what the consequences of this are in the context of a support vector machine. Concretely, what I'd like to do next is consider a case where we set this constant c to be a very large value. So let's imagine we set c to a very large value, maybe 100,000, some huge number. Let's see what a support vector machine will do. If c is very, very large, then when minimizing this optimization objective, we're going to be highly motivated to choose a value so that this first term is equal to 0. So let's try to understand the optimization problem in the context of what would it take to make this first term in the objective equal to 0, because maybe we'll set c to some huge constant. And this should give us additional intuition about what sort of hypotheses a support vector machine learns. So we saw already that whenever you have a training example with a label of y equals 1, if you want to make that first term 0, what you need is to find the value of theta so that theta transpose xi is greater than or equal to 1. And similarly, whenever we have an example with label 0, in order to make sure that the cos0 of z, in order to make sure that cost is 0, we need that theta transpose xi is less than or equal to -1. So if we think of our optimization problem as now really choosing parameters to ensure that this first term is equal to 0, what we're left with is the following optimization problem. We're going to minimize that first term 0, so c times 0, because we're going to choose parameters so that's equal to 0, plus 1/2, and then that second term. And this first term, that's c times 0, so let's just cross that out because I know that's going to be 0. And this will be subject to the constraint that theta transpose xi is greater than or equal to 1 if yi is equal to 1, and theta transpose xi is less than or equal to -1 whenever you have a negative example. And it turns out that when you solve this optimization problem, when you minimize this as a function of the parameters theta, you get a very interesting decision boundary. Concretely, if you look at a data set like this with positive and negative examples, this data is linearly separable. And by that, I mean that there exists a straight line, or there exist many different straight lines that can separate the positive and negative examples perfectly. For example, here's one decision boundary that separates the positive and negative examples. But somehow that doesn't look like a very natural one, right? Or if I draw an even worse one, here's another decision boundary that separates the positive and negative examples, but just barely. But neither of those seem like particularly good choices. The support vector machine will instead choose this decision boundary, which I'm drawing in black. And that seems like a much better decision boundary than either of the ones that I drew in magenta or in green. The black line seems like a more robust separator that just does a better job separating the positive and negative examples. And mathematically, what that does is this black decision boundary has a larger distance. That distance is called the margin. But if I draw these two extra blue lines, we see that the black decision boundary has some larger minimum distance from any of my training examples, whereas the magenta and the green lines, they come awfully close to the training examples, and that seems to do a less good job separating the positive and negative classes than my black line. And so this distance is called the margin of the support vector machine, and this gives the SVM a certain robustness because it tries to separate the data with as large a margin as possible. So the support vector machine is sometimes also called a large margin classifier, and this is actually a consequence of the optimization problem we wrote down on the previous slide. I know that you might be wondering, how is it that the optimization problem I wrote down on the previous slide, how does that lead to this large margin classifier? I know I haven't explained that yet, and in the next video I'm going to sketch a little bit of the intuition about why that optimization problem gives us this large margin classifier. But this is a useful picture to keep in mind if you're trying to understand what are the sorts of hypotheses that an SVM will choose, that is trying to separate the positive and negative examples with as big a margin as possible. I want to say one last thing about large margin classifiers and this intuition. So we worked out this large margin classification setting in the case of when C, that regularization constant, was very large, right? I think I said that to 100,000 or something. So given a data set like this, maybe we'll choose that decision boundary that separates the positive and negative examples with a large margin. Now, the SVM is actually slightly more sophisticated than this large margin view might suggest. And in particular, if all you're doing is use a large margin classifier, then your learning algorithms can be sensitive to outliers. So let's say I add an extra positive example like that shown on the screen. If you add one example, then it seems as if to separate the data with a large margin, maybe I'll end up learning a decision boundary like that, right? That is the magenta line. And it's really not clear that based on a single outlier, based on like a single example, it's really not clear that it's such a good idea to change my decision boundary from the black one over to the magenta one. So if the regularization parameter C were very large, then this is actually what the SVM will do. It'll change the decision boundary from the black to the magenta one. But if C were reasonably small, or if you were to use C not too large, then you still end up with this black decision boundary. And of course, if the data were not linearly separable, so if you had some positive examples in here, or if you had some negative examples in here, then the SVM will also do the right thing. And so this picture of a large margin classifier, that's really the picture that gives better intuition only for the case of when the regularization parameter C is very large. And just to remind you, this corresponds, C plays a role similar to 1 over lambda, where lambda is the regularization parameter we had previously, and so it's only if 1 over lambda is very large, or equivalently if lambda is very small, that you end up with things like this magenta decision boundary. But in practice, when applying support vector machines, when C is not very, very large like that, it can do a better job ignoring a few outliers like here, and it'll also do reasonable things even if your data is not linearly separable. But when we talk about bias and variance in the context of support vector machines, which we'll do a little bit later, hopefully all of these trade-offs involving the regularization parameter will become clearer at that time. So I hope that gives some intuition about how the support vector machine functions as a large margin classifier that tries to separate the data with a large margin. Technically, this picture or this view is true only when the parameter c is very large, but it's a useful way to think about support vector machines. There was one missing step in this video, which is why is it that optimization problem we wrote down on these slides, how does that actually lead to the large margin classifier? I didn't do that in this video. In the next video, I will sketch a little bit more of the math behind that to explain that step in the reasoning of how the optimization problem we wrote out results in a large margin classifier. In this video, I'd like to tell you a bit about the math behind large margin classification. This video is optional, so please feel free to skip it, but it may also give you better intuition about how the optimization problem of the support vector machine, how that leads to large margin classifiers. In order to get started, let me first remind you of a couple properties of what vector inner products look like. Let's say I have two vectors u and v that look like this, so both two-dimensional vectors. Then let's see what u transpose v looks like. And u transpose v is also called the inner product between the vectors u and v. U is a two-dimensional vector, so I can plot it on this figure. So let's say that's the vector u. And what I mean by that is if on the horizontal axis, that value takes whatever value u1 is, and on the vertical axis, the height of that is whatever u2 is, the second component of the vector u. Now, one quantity that would be nice to have is the norm of the vector u. So these are double bars on the left and right that denotes the norm or the length of u. So this just means really the Euclidean length of the vector u, and this, by Pythagoras theorem, is just equal to u1 squared plus u2 squared square root, right? And this is the length of the vector u. That's a real number. So it says, what is the length of this? What is the length of this vector down here? What is the length of this arrow that I just drew is the norm of u. Now, let's go back and look at the vector v, because we want to compute the inner product. So v will be some other vector with some value v1, v2, and so the vector v will look like that. So we'll draw v like so. Now, let's go back and look at how to compute the inner product between u and v. Here's how you can do it. We're going to take the vector v and project it down onto the vector u. So I'm going to take a orthogonal projection, or a 90-degree projection, so project it down onto u like so. And what I'm going to do is measure the length of this red line that I just drew here. So I'm going to call the length of that red line p. So p is the length, or is the magnitude, of the projection of the vector v onto the vector u. Right? So let me just write that down. So p is the length of the projection of the vector v onto the vector u. And it's possible to show that the inner product u transpose v, that this is going to be equal to p times the norm, or the length, of the vector u. So this is one way to compute the inner product. And if you actually do the geometry and figure out what p is and figure out what the norm of u is, this should give you the same answer as the other way of computing the inner product, right? Which is if you take u transpose v, then u transpose is this u1, u2 is a 1/2 matrix, and then times v, and so this should actually give you u1 v1 plus u2 v2. And it's sort of a theorem of linear algebra that these two formulas give you the same answer. And by the way, u transpose v is also equal to v transpose u. So if you were to do the same process in reverse, instead of projecting v onto u, you could project u onto v, then do the same process but with the rows of u and v reversed, and you should actually get the same number, whatever that number is. And just to clarify what's going on in this equation, the norm of u is a real number, and p is also a real number, and so u transpose v is the regular multiplication of two real numbers of the length of p times the norm of u. Just one last detail, which is if you look at the norm of p, p is actually signed, so right, and it can be either positive or negative. So let me say what I mean by that. If u is a vector that looks like this, and if v is a vector that looks like this, so if the angle between u and v is greater than 90 degrees, then if I project v onto u, what I'll get is a projection that looks like this. And so I'm going to have that length p, and in this case I will still have that u transpose v is equal to p times the norm of u, except that in this example p will be negative. So in inner products, if the angle between u and v is less than 90 degrees, then p is the positive length of that red line, whereas if this angle here is greater than 90 degrees, then p here will be negative of the length of this little line, of that little line segment over there. And so the inner product between two vectors can also be negative if the angle between them is greater than 90 degrees. So that's how vector inner products work. We're going to use these properties of vector inner product to try to understand the support vector machine optimization objective a little better. Here's the optimization objective for the support vector machine that we worked out earlier. Just for the purpose of this slide, I'm going to make one simplification, just to make the objective easy to analyze. And what I'm going to do is ignore the intercept terms. We'll just ignore theta 0 and set that to be equal to 0. To make things easy to plot, I'm also going to set n, the number of features, to be equal to 2. So we have only two features, x1 and x2. Now let's look at the objective function, the optimization objective of the SVM. When we have only two features, when n is equal to 2, this can be written 1/2 of theta 1 squared plus theta 2 squared, because we only have two parameters, theta 1 and theta 2. And what I'm going to do is rewrite this a bit. I'm going to write this as 1/2 of theta 1 squared plus theta 2 squared, and then square root squared. And the reason I can do that is because for any number, w, right, the square roots of w and then squared, that's just equal to w. So square roots and squared, and it should give me the same thing. And what you may notice is that this term inside the parentheses, that's equal to the norm or the length of the vector theta. And what I mean by that is that if we write out the vector theta like this, that's theta 1, theta 2, then this term that I've just underlined in red, that's exactly the length or the norm of the vector theta, following the definition of the norm of a vector that we had on the previous slide. And in fact, this is actually equal to the length of the vector theta, whether we write it as theta 0, theta 1, theta 2, that is if theta 0 is equal to 0, as I assume here, or just the length of theta 1, theta 2. But for this line, I'm going to ignore theta 0. So let me just treat theta as this, let me just write theta, the norm of theta, as this theta 1, theta 2 only. But the math works out either way, whether we include theta 0 here or not. So it's not going to matter for the rest of our derivation. And so finally, this means that my optimization objective is equal to 1/2 of the norm of theta squared. So all the support vector machine is doing in the optimization objective is minimizing the squared norm or the squared length of the parameter vector theta. Now what I'd like to do is look at these terms, theta transpose x, and understand better what they're doing. So given a parameter vector theta and given an example x, what is this equal to? And on the previous slide, we figured out what u transpose v looks like for different vectors u and v, and so we're going to take those definitions with theta and xi playing the roles of u and v, and let's see what that picture looks like. So let's say I look at just a single training example. Let's say I have a positive example that drawing is across there, and let's say that's my example xi, right? So what that really means is that I've plotted on the horizontal axis some value xi1, and on the vertical axis xi 2. That's how I plot my training examples. And although we haven't been really thinking of this as a vector, what this really is, this is a vector from the origin, from 0, 0, out to the location of this training example. And now, let's say we have a parameter vector theta, and I'm going to plot that as a vector as well. And what I mean by that is I'm going to plot theta 1 here, and theta 2 there. So what is the inner product, theta transpose xi? Well, using our earlier method, the way we compute that is we take my example and project it onto my parameter vector theta, and then I'm going to look at the length of this segment that I'm coloring in red, and I'm going to call that P superscript I to denote that this is a projection of the ith training example onto the parameter vector theta. And so what we have is that theta transpose xi is equal to, following what we had on the previous slide, this is going to be equal to P times the length or the norm of the vector theta. And this is of course also equal to theta 1 x1 plus theta 2 x2. So each of these, is an equally valid way of computing the inner product between theta and xi. Okay, so where does this leave us? What this means is that these constraints, that theta transpose xi be greater than or equal to 1, or there's less than or equal to minus 1, what this means is I can replace these with constraints that pi times x be greater than or equal to 1, because theta transpose xi is equal to pi times the norm of theta. So writing that into our optimization objective, this is what we get, where I have, instead of theta transpose xi, I now have this pi times the norm of theta. And just to remind you, we worked out earlier too that this optimization objective, that can be written as 1/2 times the norm of theta squared. So now let's consider the training example that we have at the bottom. And for now, continuing to use the simplification that theta 0 is equal to 0, let's see what decision boundary the support vector machine will choose. Here's one option. Let's say the support vector machine were to choose this decision boundary. This is not a very good choice because it has very small margin. This decision boundary comes very close to the training examples. Let's see why the support vector machine will not do this. For this choice of parameters, it's possible to show that the parameter vector theta is actually at 90 degrees to the decision boundary. And so that green decision boundary corresponds to a parameter vector theta that points in that direction. And by the way, the simplification that theta 0 equals 0, that just means that the decision boundary has to pass through the origin 0, 0 over there. So now let's look at what this implies for the optimization objective. Let's say that this example here, let's say that's my first example, x1. If we look at the projection of this example onto my parameters theta, that's the projection. And so that little line red segment, that is equal to P1. And that's going to be pretty small, right? And similarly, if this example here, if this happens to be x2, that's my second example, then if I look at the projection of this example onto theta, then let me draw this one in magenta. This little magenta line segment, that's going to be P2. That's the projection of the second example onto the direction of my parameter vector theta, which goes like this. And so this little projection line segment is going to be pretty small. P2 will actually be a negative number, right? So P2 will be because it's in the opposite direction. This vector has greater than 90-degree angle with my parameter vector theta, it's going to be less than 0. And so what we're finding is that these terms pi and are going to be pretty small numbers. And so if we look at the optimization objective and see, well, for positive examples, we need pi times the norm of theta to be bigger than or equal to 1. But if pi over here, if p1 over here is pretty small, that means that we need the norm of theta to be pretty large, right? Because if P1 of theta is small and we want P1 times the norm of theta to be bigger than or equal to 1, well, the only way for that to be true, for the product of these two numbers to be large, if P1 is small, is if we set norm of theta to be large. And similarly, for our negative example, we need P2 times the norm of theta to be less than or equal to -1. And we saw in this example, right, that P2 is going to be a pretty small negative number. And so the only way for that to happen as well is for the norm of theta to be large. But what we're doing in the optimization objective is we're trying to find a setting of parameters where the norm of theta is small. And so, so this doesn't seem like such a good direction for the parameter vector theta. In contrast, let's look at a different decision boundary. Here, let's say this SVM chooses that decision boundary. Now the picture is going to be very different. If that's the decision boundary, here's the corresponding direction for theta. So with the decision boundary, being that vertical line, that corresponds to, it's possible to show using linear algebra that the way to get that green decision boundary is to have the vector theta be at 90 degrees to it. And now, if you look at the projection of your data onto the vector x, let's say as before that this example is my example x1. So when I project this onto x, onto theta, what I find is that this is P1, that length there is P1, and from other example, if that example is x2, and I do the same projection, then what I find is that this length here is P2. Really, this is going to be less than 0. And you notice that now P1, right, and P2, these lengths of the projections are going to be much bigger. And so if we still need to enforce these constraints that P1 of the norm of theta is greater than or equal to 1, because P1 is so much bigger now, the norm of theta can be smaller. And so what this means is that by choosing the decision boundary shown on the right instead of on the left, the SVM can make the norm of the parameters theta much smaller. So if it can make the norm of theta smaller and therefore make the squared norm of theta smaller, which is why the SVM would choose this hypothesis on the right instead. And this is how the SVM gives rise to this large margin classification effect. Namely, if you look at this green line, if you look at this green hypothesis, we want the projections of my positive and negative examples onto theta to be large, and the only way for that to hold true is if, surrounding this green line, there's this large margin, there's this large gap that separates the positive and negative examples, and there's really the magnitude of this gap, the magnitude of this margin is exactly the values of P1, P2, P3, and so on. And so is by making the margin large, or by making these terms P1, P2, P3, and so on, that the SVM can end up with a smaller value for the norm of theta, which is what it's trying to do in the objective. And this is why the support vector machine ends up with a large margin classifier, is because it's trying to maximize the norm of these PIs, which is the distance from the training examples to your decision boundary. Finally, we did this whole derivation using this simplification that the parameter theta 0 must be equal to 0. The effect of that, as I mentioned briefly, is that if theta 0 is equal to 0, what that means is that we're entertaining only decision boundaries that pass through the origin, so decision boundaries that pass through the origin like that. If you allow theta 0 to be non-zero, then what that means is that you entertain decision boundaries that do not pass through the origin, like that one that I just drew. And I'm not going to do the full derivation, but it turns out that the same large margin proof works pretty much in exactly the same way. And there's a generalization of this argument that we just went through, that I'm not going to go through, that shows that even when theta 0 is non-zero, what the SVM is trying to do when you have this optimization objective, which again corresponds to the case of when C is very large, But it's possible to show that even when theta 0 is not equal to 0, the support vector machine is really trying to find a large margin separator between the positive and the negative examples. So that explains how the support vector machine is a large margin classifier. In the next video, we'll start to talk about how to take some of these SVM ideas and start to apply them to building complex nonlinear classifiers as well. In this video, I'd like to start adapting support vector machines in order to develop complex nonlinear classifiers. The main technique for doing that is something called kernels. Let's see what these kernels are and how to use them. If you have a training set that looks like this, and you want to find a nonlinear decision boundary to distinguish the positive and negative examples, maybe a decision boundary that looks like that. One way to do so is to come up with a set of complex polynomial features, right? So a set of features that looks like this, so that you end up with a hypothesis X that predicts 1 if, that theta 0 plus theta 1 x1 plus ... all those polynomial features is greater than 0, and predicts 0 otherwise. And another way of writing this, to introduce a little bit of new notation that I'll use later, is that we can think of a hypothesis as computing a decision boundary using this. So theta 0 plus theta 1 f1 plus theta 2 f2 plus theta 3 f3 plus and so on, where I'm going to use this new notation f1, f2, f3 and so on to denote these new sort of features that I'm computing. So f1 is just equal to x1, f2 is equal to x2, f3 is equal to this thing here, so x1, x2, f4 is equal to x1 squared, f5 is equal to x2 squared, and so on. And we've seen previously that coming up with these high order polynomials is one way to come up with lots more features. But the question is there a different choice of features, or is there a better choice of features than these high order polynomials? Because, it's not clear that these high order polynomials is what we want. And when we talked about computer vision, talked about when the input is an image with lots of pixels, we also saw how using high order polynomials becomes very computationally expensive because there are a lot of these high order polynomial terms. So is there a different or a better choice of the features that we can use to plug into this sort of hypothesis form? So here's one idea for how to define new features f1, f2, f3. On this slide, I'm going to define only 3 new features, but for real problems, we're going to define a much larger number. But here's what I'm going to do. In this space of features, x1, x2, and I'm going to leave x0 out of this, the intercept term x0, but in this space, x1, x2, I'm going to just, manually pick a few points. I'm going to call this point L1. I'm going to pick a different point. Let's call that L2, and let's pick a third one. I'm going to call this one L3. And for now, let's just say that I'm going to choose these 3 points manually. I'm going to call these 3 points landmarks. So I have landmark 1, 2, 3. What I'm going to do is define my new features as follows. Given an example X, let me define my first feature, F1, to be some measure of the similarity between my training example X and my first landmark. And the specific formula that I'm going to use to measure similarity is going to be this, is e to the minus the length of x minus L1 squared divided by 2 sigma squared. So depending on whether or not you watched the previous optional video, this notation, right? This is the length of the vector w, and so this thing here, this x minus L1, this is actually just the Euclidean distance, squared, is the Euclidean distance between the point x and the landmark L1. I'll say more about this later. But that's my first feature, and my second feature, F2, is going to be similarity function that measures how similar x is to L2, and again is going to be defined as the following function. So it's e to the minus of the square of the Euclidean distance between x and the second landmark. That's what that numerator is.
and then divided by 2 sigma squared. And similarly, f3 is, similarity between x and L3, which is equal to, again, similar formula. And what this similarity function is, the mathematical term for this is that this is going to be a kernel function. And the specific kernel that I'm using here, this is actually called a Gaussian kernel. And so this formula, this particular choice of similarity function is called a Gaussian kernel. But the way the terminology goes is that, in the abstract, these different similarity functions are called kernels, and we can have different similarity functions. And the specific example I'm giving here is called a Gaussian kernel. We'll see other examples of other kernels, but for now, just think of these as similarity functions. And so instead of writing similarity between x and L, sometimes we'll also write this as a kernel denoted, lowercase k between x and one of my landmarks, Li. So let's see what these kernels actually do, and why these sorts of similarity functions, why these e to the so on expressions might make sense. So let's take my first landmark, my landmark L1, which is one of those points I chose on my figure just now. So the similarity of the kernel between x and L1 is given by this expression. Just to make sure we're on the same page about what the numerator term is, the numerator can also be written as a sum from j equals 1 through n of sort of the distance. So this is the component-wise distance between the vector x and the vector L. And again, for the purpose of these slides, I'm ignoring x0, so just ignoring the intercept term x0, which is always equal to 1. So this is how you compute the kernel, or the similarity between x and a landmark. So let's see what this function does. Suppose x is close to one of the landmarks. Then this Euclidean distance formula in the numerator will be close to 0, right? So that is this term here, the distance, or the square distance between x and L will be close to 0. And so f1, this feature will be approximately e to the minus 0 in the numerator squared over 2 sigma squared. So then e to the 0, e to the minus 0, e to the 0 is going to be close to 1. Okay, and I put the approximation symbol here because, the distance may not be exactly 0, but if x is close to the landmark, this term will be close to 0, and so f1 will be close to 1. Conversely, if x is far from L1, then this first feature, f1, will be e to the minus of some large number squared divided by 2 sigma squared, and e to the minus of a large number is going to be close to 0. So what these features do is they measure how similar x is from one of your landmarks, and the feature f is going to be close to 1 when x is close to your landmark, and it's going to be 0 or close to 0 when x is far from your landmark. And each of these landmarks, on the previous slide I drew 3 landmarks, L1, L2, L3. Each of these landmarks defines a new feature, F1, F2, F3. That is, given a training example x, we can now compute 3 new features, F1, F2, F3, given the 3 landmarks that I wrote out just now. But first, let's look at this exponentiation function. Let's look at the similarity function and plot it in figures and just understand better what this really looks like. For this example, let's say I have 2 features, x1 and x2, and let's say my first landmark L1 is at a location 3, 5. So, and let's say I set sigma squared equals 1 for now. If I plot what this feature looks like, what I get is this figure. So the vertical axis, the height of the surface, is the value of f1, and down here on the horizontal axes are, if I have some training example, and that's x1 and that's x2, given a certain training example, if I have a training example here for a certain value of x1 and x2, right, the height above the surface shows the corresponding value of f1. And down below is the same figure shown using a contour plot with x1 on the horizontal axis, x2 on the horizontal axis, and so this figure on the bottom is just a contour plot of this 3D surface. You notice that when x is equal to 3, 5 exactly, then the f1 takes on the value 1 because that's at its maximum, and as x moves away, as x goes further away, then this feature takes on values that are close to 0. And so this is really a feature. F1 measures how close x is to the first landmark, and it varies between 0 and 1 depending on how close x is to the first landmark, L1. Now, the other thing I want to do on this slide is show the effects of varying this parameter sigma squared. So sigma squared is a parameter of the Gaussian kernel, and as you vary it, you get slightly different effects. Let's set sigma squared to be equal to 0.5 and see what we get. If we set sigma squared to 0.5, what you find is that the kernel looks similar, except that the width of this bump becomes narrower. The contours shrink a bit too. So if sigma squared equals 0.5, then as you start from x equals 3,5, and as you move away, then the feature f1 falls to 0 much more rapidly. And conversely, if you were to increase sigma squared, so here I've set sigma squared equals 3, in that case, as I move away from L, so this point here is really L, right? As L1 is at location 3, 5, right? So shown up here. And if sigma squared is large, then as you move away from from L1, the value of the feature falls away much more slowly. So given this definition of the features, let's see what sorts of hypotheses we can learn. Given a training example X, we're going to compute these features F1, F2, F3, and our hypothesis is going to predict 1 when theta 0 plus theta 1 F1 plus theta 2 F2 and so on is greater than or equal to 0. For this particular example, let's say that I've already run a learning algorithm, and let's say that somehow I ended up with these values of the parameters. So theta 0 equals minus 0.5, theta 1 equals 1, theta 2 equals 1, and theta 3 equals 0. And what I want to do is consider what happens if we have a training example that takes that has a location at this magenta dot, right, where I just drew this dot over here. So let's say I have a training example X. What will my hypothesis predict? Well, if I look at this formula, because my training example X is close to L1, we have that F1 is going to be close to 1. But because my training example X is far from L2 and L3, I'll have that F2 will be close to 0 and F3 will be close to 0. So if I look at that formula, I have theta 0 plus theta 1 times 1 plus theta 2 times some value, not exactly 0, but let's say close to 0, and then plus theta 3 times something close to 0. And this is going to be equal to, plugging in these values now, so that gives minus 0.5 plus 1 times 1, which is 1, and so on, which is equal to 0.5, which is greater than or equal to 0. So at this point, we're going to predict y equals 1, because that's greater than or equal to 0. Now let's take a different point. Now let's say I take a different point. I'm going to draw this one in a different color, in cyan, say. For a point out there, if that were my training example X, then if you make a similar computation, you find that F1, F2, F3 are all going to be close to 0. And so we have theta 0 plus theta 1, F1, plus so on. And this will be about equal to minus 0.5, because I guess theta 0 is minus 0.5, and then F1, F2, F3 are all 0. So this will be minus 0.5. This is less than 0. And so at this point out there, we're going to predict y equals 0. And if you do this yourself for a range of different points, you should convince yourself that if you have a training example that's close to L2, say, then at this point, we'll also predict y equals 1. And in fact, what you end up doing is, if you look around this decision bound, this space, what we'll find is that for points near L1 and L2, we end up predicting positive, and for points far away from L1 and L2, that is for points far away from these two landmarks, we end up predicting that the cost is equal to 0. And so what we end up doing is that the decision boundary of this hypothesis will end up looking something like this, where inside this red decision boundary we predict y equals 1, and outside we predict y equals 0. And so this is how, with this definition of the landmarks and of the kernel function, we can learn a pretty complex nonlinear decision boundary like what I just drew, where we predict positive when we're close to either one of the two landmarks, and we predict negative when we're very far away from any of the landmarks. And so this is part of the idea of kernels and how we use them with a support vector machine, which is that we define these extra features using landmarks and similarity functions to learn more complex nonlinear classifiers. So hopefully that gives you a sense of the idea of kernels and how we can use it to define new features for the support vector machine. But there are a couple questions that we haven't answered yet. One is, how do we get these landmarks? How do we choose these landmarks? And another is, what other similarity functions, if any, can we use other than the one we talked about, which is called the Gaussian kernel? In the next video, we'll give answers to these questions and put everything together to show how support vector machines with kernels can be a very powerful way to learn complex nonlinear functions. In the last video, we started to talk about the kernels idea and how it can be used to define new features for a support vector machine. In this video, I'd like to fill in some of the missing details and also say a few words about how to use these ideas in practice, such as how they pertain to, for example, the bias-variance trade-off in support vector machines. In the last video, I talked about the process of picking a few landmarks, L1, L2, L3, and that allowed us to define the similarity function, also called a kernel, or in this example, if you have this particular similarity function, this is a Gaussian kernel, and that allowed us to build this form of a hypothesis function. But where do we get these landmarks from? Where do we get L1, L2, L3 from? And it seems also that for complex learning problems, maybe we want a lot more landmarks than just 3 of them that we might choose by hand. So in practice, this is how the landmarks are chosen, which is that given a machine learning problem, we have some data set of some positive and negative examples. So here's the idea, which is that we're going to take the examples, and for every training example that we have, we're just going to call it we're just going to put landmarks as exactly the same locations as the training examples. So if I have one training example, if that's x1, well then I'm going to choose my first landmark to be at exactly the same location as my first training example. And if I have a different training example, x2, well, I'm going to set the second landmark to be the location of my second training example. On the figure on the right, I use red and blue dots just for illustration. The color of this figure, the color of the dots on the figure on the right is not significant. But what I'm going to end up with using this method is I'm going to end up with m landmarks. So I have L1, L2, down to Lm if I have m training examples, with one landmark per location of my each of my training examples. And this is nice because it's saying that my features are basically going to measure how close an example is to one of the things I saw in my training set. So just to write this out a little more concretely, given m training examples, I'm going to choose the location of my landmarks to be exactly the locations of my m training examples. When you're given an example X, and this example X can be something in the training set, it can be something in the cross-validation set, or it can be something in the test set. Given an example X, I'm going to compute these features as so, F1, F2, and so on, where L1 is actually equal to X1, and so on. And these then give me a feature vector, so let me write F as a feature vector. So I'm going to take these F1, F2, and so on, and just group them into a feature vector that goes down to Fm. And just by convention, if we want, we can add an extra feature F0, which is always equal to 1. So this plays a role similar to what we had previously for x0, which was our intercept term. So for example, if we have a training example xi comma yi, the features we would compute for this training example would be as follows. Given xi, we would then map it to f1i, which is the similarity. I'm going to abbreviate it as SIM instead of writing out the whole word similarity, right? And f2i equals the similarity between xi and L2, and so on down to fmi equals the similarity between xi and Lm. And somewhere in the middle, somewhere in this list, at the I components, I will actually have one feature component, which is f subscript I, which is going to be the similarity between x and Li, where Li is equal to xi. And so, Fii is just going to be the similarity between x and itself. And if you're using the Gaussian kernel, this is actually e to the minus 0 over 2 sigma squared. And so this will be equal to 1. And that's okay. So one of my features for this training example is going to be equal to 1. And then similar to what I had above, I can take all of these m features and group them into a feature vector. So instead of representing my example using xi, which is this Rn or Rn plus 1 dimensional vector, depending on whether you count the intercept term as either Rn or Rn plus 1, we can now instead represent my training example using this feature vector f. I'm going to write this f superscript I, which is going to be taking all of these things and stacking them into a vector. So f1i down to fmi, and if you want, and well, usually we'll also add this f0i, where f0i is equal to 1. And so this vector here gives me my new feature vector with which to represent my training example. So given these kernels and similarity functions, here's how we use a support vector machine. If you already have a learned set of parameters theta, then if you're given a value of x and you want to make a prediction, what we do is we compute the features f, which is now a Rm plus 1 dimensional feature vector. And we have m here because we have m training examples and thus m landmarks. And what we do is we predict 1 if theta transpose f is greater than or equal to 0, right? So theta transpose f, of course, that's just equal to theta 0, f0 plus theta 1, f1 plus dot 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 plus theta m, fm. And so my parameter vector theta is also now going to be an m plus 1 dimensional vector. And we have m here because the number of landmarks is equal to the training set size. So m was the training set size, and now the parameter vector theta is going to be m plus 1 dimensional. So that's how you make a prediction if you already have a setting for the parameters theta. How do you get the parameters theta? Well, you do that using the SVM learning algorithm. And specifically, what you do is you would solve this minimization problem. You minimize the parameters theta of c times this cost function which we had before. Only now, instead of looking there, instead of making predictions using theta transpose xi, using our original features xi, instead we've taken the features xi and replaced them with the new features. So we're using theta transpose fi to make a prediction on the IVE training example, and we see that in both places here. And it's by solving this minimization problem that you get the parameters for your support vector machine. And one last detail is because for this optimization problem, we really have n equals m features. That is, here the number of features we have in really the effective number of features we have is the dimension of f, so that n is actually going to be equal to m. So if you want to, you can think of this as a sum. This really is a sum from j equals 1 through m. And one way to think about this is you can think of it as n being equal to m, because if f is new features, then we have m plus 1 features, with the plus 1 coming from the intercept term. And here we still do sum from j equals 1 through m, because similar to our earlier videos on regularization, we still do not regularize the parameter theta 0, which is why this is a sum from j equals 1 through m instead of j equals 0 through m. So that's the support vector machine learning algorithm. There's one sort of mathematical detail aside that I should mention, which is that in the way a support vector machine is implemented, this last term is actually done a little bit differently. So you don't really need to know about this last detail in order to use support vector machines, and in fact the equation that I've written down here should give you all the intuitions that you need. But in the way a support vector machine is implemented, that term, the sum over j of theta j squared, right? Another way to write this is can be written as theta transpose theta if we ignore the parameter theta 0. So if theta were, theta 1 down to theta m, ignoring theta 0, then this sum over j of theta j squared, this can also be written theta transpose theta. And what most support vector machine implementations do is actually replace this theta transpose theta with instead theta transpose times some matrix inside that depends on the kernel you use times theta. And so this gives us a slightly different distance metric. Like this is a slightly different measure of instead of minimizing exactly the norm of theta squared, we instead minimize something slightly similar to it. That's like a rescaled version of the parameter vector theta that depends on the kernel. But this is kind of a mathematical detail that allows the support vector machine software to run much more efficiently. And the reason the support vector machine does this is with this modification, it allows it to scale to much bigger training sets. Because, for example, if you have a training set with 10,000 training examples, then the way we define landmarks, we end up with 10,000 landmarks, and so theta becomes 10,000 dimensional. Maybe that'll work, but when n becomes really, really big, then solving for all of these parameters, if n were 50,000 or 100,000, then solving for all of these parameters can become expensive for the support vector machine optimization software. That's solving the minimization problem that I drew here. So kind of as a mathematical detail, which again you really don't need to know about, it actually modifies that last term a little bit to optimize something slightly different than just minimizing the norm squared of theta. But if you want, you could feel free to think of this as kind of a implementational detail that does change the objective a bit, but is done primarily for reasons of computational efficiency. So you usually don't really have to worry about this. And by the way, in case you're wondering why we don't apply the kernels idea to other algorithms as well, like logistic regression, it turns out that if you want, you can actually apply the kernels idea and define these sorts of features using landmarks and so on for logistic regression, but the computational tricks that apply for support vector machines don't generalize well to other algorithms like logistic regression, and so using kernels with logistic regression is going to be very slow, whereas because of computational tricks like that embodied in how it modifies this and the details of how the support vector machine software is implemented, support vector machines and kernels tend to go particularly well together, whereas logistic regression and kernels, you can do it, but it's going to run very slowly, and it won't be able to take advantage of advanced optimization techniques that people have figured out for the particular case of running a support vector machine with a kernel. But all this pertains only to how you actually implement software to minimize the cost function. I'll say more about that in the next video, but you really don't need to know about how to write software to minimize this cost function, because you can find very good off-the-shelf software for doing so. And just as I wouldn't recommend writing code to invert a matrix or to compute the square root, I actually do not recommend writing software to minimize this cost function yourself, but instead to use off-the-shelf software packages that people have developed. And so those software packages already embody these numerical optimization tricks. And so you don't really have to worry about them. But one other thing that is worth knowing about is when you're applying a support vector machine, how do you choose the parameters of the support vector machine? And the last thing I want to do in this video is say a little bit about the bias and variance trade-offs when using a support vector machine. When using an SVM, one of the things you need to choose is the parameter C, which was in our optimization objective. And you recall that C played a role similar to 1 over lambda, where lambda was the regularization parameter we had for logistic regression. So if you have a large value of C, this corresponds to what we had back in logistic regression of a small value of lambda, meaning of not using much regularization. And if you do that, you tend to have a hypothesis with lower bias and higher variance. Whereas if you use a smaller value of C, then this corresponds to when we're using logistic regression with a large value of lambda, and that corresponds to a hypothesis with higher bias and lower variance. And so a hypothesis with large C has a higher variance and is more prone to overfitting, whereas a hypothesis with small c has a higher bias and is thus more prone to underfitting. So this parameter c is one of the parameters we need to choose. The other one is the parameter sigma squared, which appeared in the Gaussian kernel. So if the Gaussian kernel sigma squared is large, then in the similarity function, which was this, e to the minus x minus landmark, right, I squared over 2 sigma squared. In this 1D example, if I have only one feature x1, if I have a landmark there at that location, if sigma squared is large, then the Gaussian kernel will tend to fall off relatively slowly, and so this would be my feature fi, and so this would be a smoother function that varies more smoothly, and so this would give me a hypothesis with higher bias and lower variance. Because the Gaussian kernel that falls off smoothly, you tend to get a hypothesis that varies slowly or very smoothly as you change the input x. Whereas in contrast, if sigma squared was small, then if that's my landmark, and given my one feature x1, my Gaussian kernel, my similarity function, will vary more abruptly. In both cases of peak at 1. And so if sigma squared is small, then my features vary less smoothly. So if I just have higher slopes, higher derivatives here, and using this, you end up fitting hypotheses of lower bias, and you can have higher variance. And if you look at this week's programming exercise, you actually get to play around with some of these ideas yourself and see these effects yourself. So that was the support vector machine with Kernels algorithm, and hopefully this discussion of bias and variance will give you some sense of how you can expect this algorithm to behave as well. So far we've been talking about SVMs at a fairly abstract level. In this video, I'd like to talk about what you actually need to do in order to run or to use an SVM. The support vector machine algorithm poses a particular optimization problem, but as I briefly mentioned in an earlier video, I really do not recommend writing your own software to solve for the parameters data yourself. So just as today, very few of us, or maybe almost essentially none of us, would think of writing code ourselves to invert a matrix or take the square root of a number and so on. You just call some library function to do that. In the same way, the software for solving the SVM optimization problem is very complex, and there have been researchers that have been doing essentially numerical optimization research for many years to come up with good software libraries and good software packages to do this. And I strongly recommend just using one of the highly optimized software libraries rather than trying to implement something yourself. And there are lots of good software libraries out there. The two that I happen to use the most often are liblinear and libsvm, but there are really lots of good software libraries for doing this that you can link to many of the major programming languages that you may be using to code up a learning algorithm. Even though you shouldn't be writing your own SVM optimization software, there are a few things you need to do though. First is to come up with some choice of the parameter c. We talked a little bit about the bias variance properties of this in an earlier video. Second, you also need to choose the kernel or the similarity function that you want to use. So one choice might be if you decide not to use any kernel, and the idea of no kernel is also called a linear kernel. So if someone says, I use an SVM with a linear kernel, what that means is, they use an SVM without using a kernel, and it was a version of the SVM that just uses theta transpose x, right? That predicts 1 if theta 0 plus theta 1 x1 plus so on plus theta n xn is greater than or equal to 0. And this term linear kernel, you can think of this as, this is a version of the SVM that just gets you a standard linear classifier. So that would be one reasonable choice for some problems, and there would be many software libraries like liblinear was one example out of many. Is one example of a software library that can train an SVM without using a kernel, also called a linear kernel. So when would you want to do this? Well, if you have a large number of features, if n is large, and m, the number of training examples, is small, then you have a huge number of features. If x is in Rn or Rn plus 1, so if you have a huge number of features already with a small training set, maybe you want to just fit a linear decision boundary and not try to fit a very complicated nonlinear function, because you might not have enough data and you might risk overfitting if you're trying to fit a very complicated function in a very high dimensional feature space, but if your training set is small. So this would be one reasonable setting where you might decide to just not use a kernel, or equivalent to use what's called a linear kernel. A second choice for the kernel that you might make is this Gaussian kernel, and this is what we had previously. And if you do this, then the other choice you need to make is to choose this parameter sigma squared, when we also talk a little bit about the bias variance trade-offs of how if sigma squared is large, then you tend to have a higher bias, lower variance classifier. But if sigma squared is small, then you have a higher variance, lower bias classifier. So when might you choose the Gaussian kernel? Well, if your original features x are in Rn, and if n is small, and ideally, if m is large, right? So that's if we have, say, a two-dimensional training set, like the example I drew earlier. So n is equal to 2, but we have a pretty large training set. So I've drawn in a fairly large number of training examples. Then maybe you want to use a kernel to fit a more complex nonlinear decision boundary, and the Gaussian kernel would be a fine way to do this. I'll say more towards the end of the video, a little bit more about when you might choose a linear kernel or a Gaussian kernel and so on. But concretely, if you decide to use a Gaussian kernel, then here's what you need to do. Depending on what support vector machine software package you use, it may ask you to implement a kernel function or to implement the similarity function. So if you're using an Octave or MATLAB implementation of an SVM, it may ask you to provide a function to compute a particular feature of the kernel. So this is really computing f subscript I for one particular value of I, where f here is just a single real number, right? So maybe this is better written fi. But what you need to do is write a kernel function that takes as input, a training example or a test example, whatever. It takes in some vector x and takes as input one of the landmarks, and but only I'm calling them x1 and x2 here because the landmarks are really training examples as well. But what you need to do is write software that takes as input, x1, x2, and computes this sort of similarity function between them and return a real number. And so what some support vector machine packages will do is expect you to provide this kernel function that takes as input, x1, x2, and returns a real number, and then it will take it from there, and it will automatically generate all the features. So automatically, take x and map it to f1, f2, down to fm using this function that you write, and generate all the features and train the support vector machine from there. But sometimes you do need to provide this function yourself. Although if you're using the Gaussian kernel, some SVM implementations will also include the Gaussian kernel and a few other kernels as well, since the Gaussian kernel is probably the most common kernel. Gaussian and the linear kernels are really the two most popular kernels by far. Just one implementational note: if you have features on very different scales, it is important to perform feature scaling before using the Gaussian kernel. And here's why. If you imagine computing the norm between x and L, right? So this term here is sort of like the numerator term over there. What this is doing, the norm between x and L, that's really saying, let's compute a vector v, which is equal to x minus L, and then let's compute, right, the norm of this vector v, which is the difference between x and L. And so the norm of v is really equal to v1 squared plus v2 squared plus dot 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 plus vn squared, because here x is in Rn or Rn plus 1, but I'm going to ignore x0. So let's pretend x is in Rn and put a square on the left side as well to make this correct. And so this is equal to that, right? And so written differently, this is going to be x1 minus L1 squared plus x2 minus L2 squared plus dot 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 plus xn minus Ln squared. And now if your features take on very different ranges of values. So take a housing prediction example. You're trying to, if your data is some data about houses, and if X is in the range of thousands of square feet, right? But for the first feature x1, but if your second feature x2 is the number of bedrooms, so if this is in the range of 1 to 5 bedrooms, then x1 minus L1 is going to be huge. This could be like 1,000 squared, whereas x2 minus L2 is going to be much smaller. And if that's the case, then in this term, those distances will be almost essentially dominated by the sizes of the houses, and the number of bedrooms will be largely ignored. And so to avoid this, in order to make an SVM work well, perform feature scaling, and that will make sure that the SVM gives comparable amount of attention to all of your different features, and not just to, in this example, the size of the houses, while ignoring the other features. When you're applying a support vector machine, chances are by far the two most common kernels you use will be the linear kernel, meaning no kernel, or the Gaussian kernel that we talked about. And just one note of warning, which is that not all similarity functions you might come up with are valid kernels. And the Gaussian kernel and the linear kernel and other kernels that sometimes others will use, all of them need to satisfy a technical condition. It's called Mercer's theorem. And the reason they need to do this is because support vector machine algorithms or implementations of the SVM have lots of clever numerical optimization tricks in order to solve for the parameters theta efficiently. And in the original design of SVMs, there was a decision made to restrict our attention only to kernels that satisfy this technical condition called Mercer's theorem. And what that does is that makes sure that all of these SVM packages, all of these SVM software packages, can use a large class of optimizations and get the parameter theta very quickly. So what most people end up doing is using either the linear or the Gaussian kernel. But there are a few other kernels that also satisfy Mercer's theorem and that you may run across other people using, although I personally end up using other kernels, very, very rarely, if at all. Just to mention some of the other kernels that you may run across, one is the polynomial kernel, and for that, the similarity between X and L is defined as, there are a lot of options, I guess. You can take X transpose L squared. So here's one measure of how similar X and L are, right? If X and L are very close to each other, then the inner product will tend to be large. And so this is a slightly unusual kernel that's not used that often, but it works. But you may run across it. So there's some people using it. This is one version of the polynomial kernel. Another is X transpose L cubed, or these are all examples of the polynomial kernel. X transpose L plus 1 cubed, X transpose L plus maybe a number different than 1, like 5, and then to the power of 4. And so the polynomial kernel actually has two parameters. One is what number do you add over here? It could be 0. This is really hat plus 0 over there. As well as what's the degree of the polynomial. So the degree, the power, and this number. So the more general form of this, of the polynomial kernel, is X transpose L plus some constant, and then to some degree in the exponent. And so both of these are parameters for the polynomial kernel. So the polynomial kernel almost always or usually performs worse than the Gaussian kernel, and is not used that much, but it's just something that you may run across. Usually is used only for data where X and L are all strictly non-negative, and so that ensures that these inner products are never negative. But it captures this intuition that if X and L are very similar to each other, then maybe the inner product between them will be large. But it has some other properties as well, but people then tend not to use it much. And then depending on what you're doing, there are other sort of more esoteric kernels as well that you may come across. There's a string kernel. This is sometimes used if your input data is text strings or other types of strings. There are things like the chi-square kernel, the histogram section kernel, and so on. There's sort of more esoteric kernels that you can use to measure similarity between different objects. So, for example, if you're trying to do some sort of text classification problem where the input X is a string, then maybe you want to define the similarity between two strings using the string kernel. But I personally, end up very rarely, if at all, using these more esoteric kernels. I think I might have used the chi-square kernel maybe once in my life, and the histogram kernel maybe once or twice in my life, and I've actually never used the string kernel myself. But in case you run across this in other applications, if you do a quick web search, if you do a quick Google search or a quick Bing search, you should find definitions of these other kernels as well. So, just two last details I want to talk about in this video. One is multi-class classification. So if you have 4 classes, or more generally K classes, how do you get an SVM to output some appropriate decision boundary between your multiple classes? Many SVM packages already have built-in multi-class classification functionality. So if you're using a package like that, you just use that built-in functionality, and that should work fine. Otherwise, one way to do this is to use the one versus all method that we talked about when we were developing logistic regression. So what you do is you train K SVMs, if you have K classes, one to distinguish each of the classes from the rest, and this will give you K parameter vectors. So this will give you, theta 1, which is trying to distinguish class y equals 1 from all of the other classes. Then you get a separate parameter vector theta 2, which is what you get when you have y equals 2 as the positive class and all the others as a negative class, and so on, up to a parameter vector theta k, which is the parameter vector for distinguishing the final class k from everything else. And then lastly, this is exactly the same as the one versus all method we have for logistic regression, really. You just predict the class I with the largest theta I transpose x. So that's multi-class classification of SVMs. But the more common case is that there's a good chance that whatever software package you use, there'll be a reasonable chance that it'll already have built-in multi-class classification functionality. And so you don't even need to worry about this yourself. Finally, we developed support vector machines starting off with logistic regression and then modifying the cost function a little bit. So the last thing I want to do in this video is just say a little bit about when you would use one of these two algorithms. So let's say n is the number of features and m is the number of training examples. So when should we use one algorithm versus the other? Well, if n is large relative to your training set size, so for example, if you think of this as if the number of features is much larger than m, and this might be, for example, if you have a text classification problem where the dimension of your feature vectors, I don't know, maybe 10,000, and if your training set size is maybe 10, maybe up to 1,000, right? So imagine a spam classification problem where email spam, where you have 10,000 features corresponding to 10,000 words, but you have, maybe 10 training examples or maybe up to 1,000 examples. So if n is large relative to m, then what I would usually do is use logistic regression or use an SVM without a kernel, or use it with a linear kernel. Because if you have so many features for the smaller training set, a linear function will probably do fine, and you don't have really enough data to fit a very complicated nonlinear function. Now, if n is small and m is intermediate, so what I mean by this, if n is maybe anywhere from 1 to 1,000, 1 would be very small, but maybe up to 1,000 features, and if the number of training examples is maybe anywhere from 10 to maybe up to 10,000 examples, maybe up to 50,000 examples. So if m is pretty big, like maybe 10,000, but not a million, right? So if m is intermediate size, then often an SVM with a linear kernel will work well. We talked about this earlier as well, but one concrete example of this would be if you have a two-dimensional training set. So if n is equal to 2, but you have, drawing in a pretty large number of training examples, so a Gaussian kernel would do a pretty good job separating positive and negative classes. One third setting that's of interest is if n is small, but m is large. So if n is, again, maybe 1 to 1,000, could be larger, but if m was, maybe 50,000 and greater to millions, right? So 50,000, 100,000, million, 2 million, you can have very, very large training set sizes, right? So if this is the case, then an SVM with a Gaussian kernel will be somewhat slow to run. Today's SVM packages, if you're using a Gaussian kernel, tend to struggle a bit. If you have, maybe 50,000 is okay, but if you have a million training examples, or maybe even 100,000, with a massive value of m, today's SVM packages are very good, but they can still struggle a little bit when you have a massive, massive training set size and you're using a Gaussian kernel. So in that case, what I would usually do is try to just manually create or add more features, and then use logistic regression or an SVM without a kernel. And in case you look at this slide and you see logistic regression or SVM without a kernel, in both of these places, I kind of paired them together. Well, there's a reason for that, is that logistic regression and SVM without a kernel, those are really pretty similar algorithms. And either logistic regression or SVM without a kernel will usually do pretty similar things and give pretty similar performance. But depending on your implementational details, one may be more efficient than the other. But where one of these algorithms applies, logistic regression or SVM without a kernel, the other one is likely to work pretty well as well. But a lot of the power of the SVM is when you use different kernels to learn complex nonlinear functions. And this regime, when you have maybe up to 10,000 examples, maybe up to 50,000, and your number of features is reasonably large, maybe that's a very common regime, and maybe that's a regime where a support vector machine with a Gaussian kernel will shine and can do things that are much harder to do than with logistic regression. And finally, where do neural networks fit in? Well, for all of these problems, for all of these different regimes, a neural network or well-designed neural network is likely to work well as well. The one disadvantage, and one reason I might not sometimes use a neural network, is that for some of these problems, the neural network might be slower to train. But if you have a very good SVM implementation package, that could run faster, quite a bit faster than your neural network. And although we didn't show this earlier, it turns out that the optimization problem that the SVM has is a convex optimization problem. And so the good SVM optimization software packages will always find the global minimum or something close to it. And so for the SVM, you don't need to worry about local optima. In practice, local optima aren't a huge problem for neural networks, but they also it's just one less thing to worry about if you're using an SVM. And depending on your problem, the neural network may be slower, especially in this sort of regime, than the SVM. In case the guidelines I gave here seem a little bit vague, and if you're looking at some problems and you feel like, the guidelines are a bit vague, I'm still not entirely sure, should I use this algorithm or that algorithm? That's actually okay. When I face a machine learning problem, sometimes it's actually just not clear what is the best algorithm to use. But as we saw in earlier videos, really, the algorithm does matter, but what often matters even more is things like how much data do you have, and how skilled are you, how good are you at doing error analysis and debugging learning algorithms, figuring out how to design new features, or figuring out what other features to give your learning algorithm and so on. And often those things will matter more than are you using a logistic regression or an SVM. But having said that, the SVM is still widely perceived as one of the most powerful learning algorithms, and there is this regime of when there's a very effective way to learn complex nonlinear functions. And so I actually, together with logistic regression, neural networks, SVMs, using those three learning algorithms, you're actually, I think, very well positioned to build state-of-the-art machine learning systems for a wide range of applications. And this is another very powerful tool to have in your arsenal, one that is used all over the place in Silicon Valley or in industry and in academia to build many high-performance machine learning systems.